This is Module 2, Video 2 of EE300 Fall 2016. Zero state response and zero input response. In this video, we'll look at what we did previously regarding initial condition sources. We'll look at more detail in initial condition sources. We'll look at source transformations of initial condition sources. We'll then work through an extensive problem to detail circuit analysis, mechanics, and details. And then we'll take a summary of what we did. So previously, we had the initial condition sources in the S domain for the capacitor and inductor. For the capacitor, we had an impedance 1 over SC in series with an initial condition source of strength VC of 0, the initial voltage of the capacitor, time t equals 0, divided by S, corresponding to a constant voltage source in time. The impedance had units of 1 over SC, which is ohms. And so impedance is like ohms, it just has a complex value. We had the same kind of situation for the inductor. The impedance was S times L. The current source I sub L of 0 over S models the inductor current at t equals 0. And the units of SL again were ohms. So let's take a deeper dive into these initial condition sources. Consider the following two circuits. The top circuit, both circuits are essentially the same, except in the first circuit, upper circuit, there is no battery VA in series with the capacitor C. The switch in both opens at t equals 0, and all you can do is observe the voltage at V1 and V2 at their terminals. You just have a pair of wires sticking out of a box. So can you tell which circuit is which from V1 and from observing the two voltages V1 of t and V2 of t? Okay, for the upper circuit, the first circuit, the switch is closed for t less than 0. So the capacitor, everything's in constant conditions. The capacitor acts like an open circuit. So you see a voltage divider between the two resistors, and the voltage across the capacitor at t equals 0 is VA. At t greater than 0, at t equals 0, the switch opens. And so now the capacitor just sees the resistor R, so the voltage decays exponentially down to 0 with a time constant RC. So the voltage is VA e to the minus t over RC for t greater than or equal to 0. For the second circuit, the original lower circuit, the switch is also closed for t less than 0. So again, the capacitor is in a steady, everything's in constant state, so the capacitor acts like an open circuit. So if there's no current through the capacitor, any charge that was on the capacitor a long time ago had to have discharged by now. And so again, you have the voltage divider between the two resistors, and so the voltage across the resistor is VA, but you've got the battery there in series with the capacitor VA, so there's no voltage across the capacitor. So VC of 0 is equal to 0, but V2 is still equal to VA. When the switch opens at t equals 0, in this case, the capacitor is going to charge up to VA. If you think of the circuit there as a battery and a resistor and a capacitor in series, VC of t is labeled the way it normally would be if the capacitor were over on the right of the circuit. So the capacitor is going to charge up to VA with a time constant RC as usual. But as the capacitor charges up to VA, then the total voltage between the terminals indicated for V2 of t is going to go to 0 because you've got the constant voltage VA from the battery there. So V2 of t is going to go from VA down to 0 along the exponential e to the minus t over RC. You can't tell the difference between these two situations at the terminals. You can't distinguish between a capacitor that's got an initial voltage VA and a capacitor that's got 0 initial voltage that's in series with a constant voltage source VA. So this initial condition modeling that we had in the S domain is really a property of capacitors. It's not nothing to do with the S domain. It comes from the integral form of the device characteristic. We can think of the VC of 0 term as representing the initial condition, and the integral term as representing what the capacitor would do if there were 0 initial conditions. So in some sense, VC of 0 in the integral expression for the capacitor device characteristic is a source of strength VC of 0, and the 1 over C integral term represents the voltage across a zero state capacitor due to the current IC of t. And then when we transform those into the S domain, then the constant source, Vc of 0, turns into Vc of 0 over S, and the integral, scaled by 1 over c, turns into 1 over Sc times cap IC of S. The capacitor has two aspects then. We hook it up to something. Whatever happens due to the charging and discharging of the capacitor without any initial voltage, because of the integral term, that will characterize in the rest of the circuit as what's called a zero state response. And then you have dynamics in the rest of the circuit from the initial input alone, as if there were no initial state, and we'll call that the zero input response. As if there were no inputs, excuse me. So the inputs determine the zero state response, and the initial conditions determine the zero input response. And if there's independent, if you've got multiple capacitors and inductors, as long as they're independent, each is going to have its own effects. So we can extend this to a larger situation. We'll have the same situation with the inductor. We can think of the initial condition in the inductor, the current there corresponding to a source of strength I sub L of 0. This is in the time domain. And then the voltage, the current through the impedance, SL, or the current through the inductor part, the coil part, determined by the integral, the 0 to t v sub L of tau d divided by L. And when you take that to the Laplace domain, you get again an initial condition current, which corresponds to the constant, to the current. The IL of 0 corresponds to the initial condition current, IL of 0 over S, and now you get the impedance SL dividing VL of S to give the current component due to no initial conditions. Source transformations. We can take our series model for the capacitor in the S domain of impedance 1 over Sc in series with a voltage source Vc of 0 over S, and turn them into a parallel impedance with a current source. The current source strength would be the short circuit current, which will be CVC of 0, because you've taken Vc of 0 over S and then dividing it by 1 over Sc to give you CVC of 0 in parallel with the impedance 1 over Sc. That's a constant in the S domain. We don't really know what constants in the S domain stand for in the time domain yet, although we've talked about it. Basically, they're impulses. So basically, you have an impulse of current, which is a lump of charge corresponding to the initial voltage on the capacitor. We can do the same thing for the inductor. Here we have the current source, IL of 0 over S, going down through the inductor for the inductor initial current. When we transform that to an open circuit voltage, we get IL of 0 with a minus sign on top and a plus sign on the bottom in series with the impedance SL. And so now we've got here an impulse of voltage in the time domain, and that's sort of like a lump of magnetic flux you're putting on the coils of the inductor. Okay, let's work through a more detailed problem here. It's one of the problems on the practice problems from last week, the second order circuit. Because impedances act like resistive elements, we can use all the tools we have to solve resistive networks. So we have series and parallel combinations, voltage and current dividers, superposition, Thevenin and Norton equivalents, node and mesh. We can't do these all in one video, but let's work through a problem and apply one of these techniques to find the answer. So here's the problem from the practice problems. We're given a RLC circuit. It's not really parallel, it's not really series, but it's really series. Because again, if you do a source transformation on the current source in parallel with the resistor, you would have a voltage source in series with the resistor. So you have really a series RLC circuit. The current source is Is of t, and that's one way to solve the problem. You can do a source transformation and have a series circuit. Here we're going to do it like this, though. We've got a current source Is of t. It's 1 amp constant for t less than 0, and it's 2 e to the minus t amps for t greater than or equal to 0. 5 ohm resistor, 1 Henry inductor, 1/6 of a farad capacitance, and we've indicated reference voltage and current directions for the capacitor and the inductor. So, but the initial conditions for t less than 0, the capacitor acts like an open. So there's no current through the inductor because the capacitor is acting like an open. The inductor acts like a short. So whatever voltage is across the resistor is the same as the voltage across the capacitor. And since there's no current IL of t, then all the current from the source must be going through the resistor. So there's 5 volts across the resistor, and that must be the same 5 volts across the capacitor. By the continuity of the capacitor voltage and the inductor current, the capacitor voltage at t equals 0 must also be 5 volts, and the inductor current must be 0 amps. So when we take this circuit to the S domain, we replace the inductor by the impedance SL in parallel with the initial current divided by S. We replace the capacitor by the impedance 1 over SC in series with the initial voltage VC of 0 divided by S. We indicate the output voltage VC of S, and the input source, current source, turns into cap I sub S of S. The resistor is just R. We work with literals because we want to be able to check our work and see where we make mistakes and ensure that things work out consistently dimensionally. As we go through this problem, we're going to leave IL of 0 over S in. We know IL is 0 already. We could drop it out and make things a little easier, but it's sort of good to, when you're getting started with this, to see how these work out. You want to see how it carries through, and there's some things we'll see that are valuable to have IL of 0 there. We've already indicated that responses ought to be of the form ZSR plus ZIR, zero state response plus zero input response. You can see this from the circuit diagram. If you think in superposition terms, you've got the input current over here, and if these were 0, you would just have a voltage due to the input current. And that's indicated by this blank here. That's going to be some function of S determined by the network here. But you can also do the same thing for the current source standing for the initial condition current and for the voltage source corresponding to the initial condition voltage. So we can see from superposition on the circuit diagram, or from what we talked about earlier, that the output voltage in the S domain ought to be a superposition of something times the input current in the S domain plus something times the initial current of the inductor plus something times the initial voltage of the capacitor. So the first one of those will be the zero state response, and then the second two summed together would be the zero input response. So let's do node method. It's a very powerful and very general approach to solving circuits. Here are some practices for node. Sum the currents leaving the node. Yes, KCL says that you can add the currents entering a node and get 0, but in practice, at doing node method, you want to sum the currents leaving the node. Get used to it. It causes fewer sign errors. It's just a matter of practice because of that. When you do the current through the resistor, you're going to have V1 minus 0, and you're not going to get a minus sign unnecessarily there. And when you're thinking about the voltage drop across elements, use the voltage at this node less the voltage at the other node. So when we want the current through resistor R, we'll take V1 minus 0. When we want the current through the impedance SL, we'll take V1 minus V2 and divide by SL. It's practice. It's things you do consistently that reduces the number of errors you make. This is still going to be a bear of a problem even with good practice, but it's still worth doing good practice. So the current's leaving the node labeled V1. Minus I sub S is the current leaving through the current source. V1 over R is the current leaving through the resistor. V1 minus V2 over SL is the current leaving through the impedance SL. And IL of 0 over S is the current leaving through the current source in the inductor. The current's leaving V2 of S. V2 minus V1 over SL is the current leaving V2 through the impedance SL. Minus IL of 0 over S is the current, S domain current, leaving through the source. And then the current leaving through the capacitor is the capacitance 1 over SC, the impedance of the capacitor, is V2 minus VC of 0 over S divided by 1 over SC. Now we're going to do some algebra. First, clear out the denominators. Again, this is just practice how you do these things. We have in the second equation, we have the 1 over SC in the denominator. We can take that into the numerator. So that scales V2 of S, and then the S's cancel out, and we take that into the VC of 0 term. So we get SCV2 of S minus CVC of 0. Now the upper equation, we want to multiply every term by S times L times R on both sides. I'm going to do this, it's sort of globbed here, so it's two things we're doing here. We're doing the multiplication through, and then we're combining scale factors for V1 of S, scale factors for V2 of S, and then taking the input terms to the right-hand side. So when we do all that, we get SL plus R times V1 of S minus R times V2 of S, and then on the right-hand side, we get S times L times R times I sub S of S minus R times L times I sub L of 0. As I said, it's going to be a bear regardless of what we do. The second equation, we just multiply by S times L, all terms by S times L. Again, combining terms, so we get minus V1 of S, and the scale factor for V2 of S is S squared times LC plus 1, and then the right-hand side becomes L times I sub L of 0 plus S times L times C times V sub C of 0. This is two equations and two unknowns. You can do it by elimination. I think it's even more algebraically messy than doing it by matrix methods. So I'm going to do it by matrix methods. You can write this as a matrix equation where you have a scale factors SL plus R minus 1 S squared LC plus 1 times V1 and V2. And then the input terms go into these this column vector on the right-hand side. You can solve this using Cramer's rule. Cramer's rule says that to find the second variable of these two in this column vector of variables here, you take the determinant of the scale factor matrix with the second column replaced by the input column, and then divide that by the determinant of the scale factor matrix. So taking determinants, you multiply for 2 by 2, it's really easy. You take upper left times lower right minus lower left times upper right, etc. So we get SL plus R times this whole L I sub L of 0 plus SLC VC of 0 minus 1 times the SLR I sub S of S minus RL I sub L of 0 term. In the denominator, we get SL plus R times S squared LC plus 1 minus 1 times minus R. So, interestingly and conveniently and happily, there's an SL that factors out of every term in the numerator. And there's an SL that factors out of every term in the denominator. So I'm not going to go through every detail here. You can sit and work these out yourselves. But when we do so, we cancel the SLs out. We're left with the denominator, which is S squared times LC plus S times RC plus 1, which reminds us of things we've seen before with series RLC circuits. And in the numerator, we've got R times I sub S of S, L times I sub L of 0, and SL plus R times C VC of 0. And we write these out in a distributed form where we see a scale factor times I sub S of S, a scale factor times I sub L of 0, a scale factor times V sub C of 0. Each of them has the same denominator, yes, but we write them out separately. And we identify the first term there as a zero state response in the S domain, and the other two terms as a zero input response in the S domain. So we can do some checking here. We've already mentioned how we wrote this out. We're going to check dimensions. The voltage in the S domain is volts times seconds. We have resistance times current times seconds, so that's volts times amps seconds, so we get volts seconds. The denominator is dimensionless. This is time squared, 1 over time squared. 1 over time squared times time squared, 1 over time times time, dimensionless. Here we have inductance times I sub L of 0. Inductance has units of henries. Henries is the same thing as ohms times seconds. So again, we've got ohms times seconds times amps. So we get volt seconds, consistent with the left-hand side, denominator dimensionless. Again, we've got RC which is time, times V, gives us volts times time. And then again, S is per second, L is ohms seconds, so this has units of ohms, times C, times VC, back to volts seconds. So everything's fine dimensionally. Now we want to write the denominator with the leading coefficients of 1. So we factor out LC out of everything in numerator and denominator, or we multiply numerator and denominator by 1 over LC, however you want to look at that. And when you do that, you get this form here, which has leading coefficients of 1. And now before we can do anything else, we have to plug in the values of the input in the S domain, the initial conditions, and the component values. So here's our VC of S. Again, the three terms all have the same denominator. Here's our component values, 5 ohms, 1 Henry, and 1/6 of a farad. And so LC is 1/6, 1 over LC is 6, and R times 1 over LC is 30. So when we plug in, R over L is going to be 5. So when we plug these in, we get the denominator is S squared plus 5S plus 6. And then we get 30 in the numerator of the first term, 6 in the numerator of the second term, S plus 5 in the numerator of the third term. Now we say we had no component, the initial current was 0, the capacitor voltage at t equals 0 is 5 volts. We plug those in, so we just get a 0 and a 5. The middle term is going to drop out. And now we take the Laplace transform of the input, which was 2 e to the minus t amps. So that's 2 over S plus 1 amp seconds. And we plug that in for the input term. And we can put everything into factored form for the bottom equation here, still keeping the zero state response separate from the zero input response. So we have 60 over S plus 1 times S plus 2 times S plus 3, and then 5 times S plus 5 over S plus 2 times S plus 3. Now we can do partial fractions inverse transforming. I'm not going to work through the entire cover-up to get the various terms. You can do that on your own. So we get 30 over S plus 1, minus 60 over S plus 2, 30 over S plus 3, and then the second term expands into 15 over S plus 2 and minus 10 over S plus 3, and we can take those to the time domain. So we get 30 times e to the minus t minus 60 e to the minus 2t plus 30 e to the minus 3t for the zero state response. If there had been no capacitor voltage, no inductor, there was no inductor current to start with, and if there had been no capacitor voltage, this is what we would have gotten for that same input of 2 e to the minus t. On the other hand, if there had only been the capacitor voltage and had been no input, we would have gotten 15 e to the minus 2t minus 10 e to the minus 3t. That's the zero input response. We can further break the zero state response and notice that it has a term that looks like the input. So it's got the 30 e to the minus t along the same form as e to the minus t. That's a forced response. And then it has its own natural response with the poles of the circuit, e to the minus 2 at plus 2 and plus 3, at minus 2 and minus 3, s plus 2 and s plus 3, corresponding to the exponentials e to the minus 2 and e to the minus 3, t, e to the minus 2t, e to the minus 3t. Those are the natural response components of the zero state response. And then the fact that we had the circuit to start with, it had its poles at minus 2 and minus 3. It gives us 15 e to the minus 2t minus 10 e to the minus 3t. That's a natural response. So the zero input response always has the form of a natural response, the poles of the circuit, if you will, whereas the zero state response reflects both the poles of the circuit and the poles of the input. And we're going to talk about that more in the next meeting. We can, of course, put those all together into one thing, saying just forced and natural. And, of course, this is what we would have gotten if we had only done differential equations and applied initial conditions. We would have never been able to tease out. We'd have had to work to tease out the zero state response and the zero input response. Whereas when we do it with Laplace, with the initial condition sources, the zero state response and the zero input response fall out naturally. We like this because largely we're going to be interested in zero state responses. Zero input responses, we're going to have signals like steps that are input that have 0 for t less than 0. So there's no chance to charge any storage elements inside. So when the input, if we had just is of t equals 2 e to the minus t u of t, and everything had been 0 for t less than 0, these terms would have gone away. So in the future, we'll move more towards looking at these kind of responses, but we'll have inputs that evoke these kind of responses and don't evoke a zero input response. So to summarize, we saw nicely that the initial state could be separated out both in the time domain and the frequency domain. And that meant when we thought about the response to inputs, we would have both the response when the energy storage elements had no initial state, plus the response to whatever initial state they had on them. So we called the first one the zero state response. We called the second the zero input response. What we're going to do next is look at how the poles and zeros of the circuit interact with the poles and zeros of the input. And we'll also go back and look at what poles and zeros, how the poles in particular correspond to particular time domain features, decaying exponentials, sinusoids with exponential envelopes, and the like. So when we look at the poles and zeros, we get some sense about what's going to happen in the time domain when we do our inverse transform. This has been EE300, Fall 2016, Module 2, Video 2, Zero State Response and Zero Input Response.